Okay, then let's get started with today's lecture. Just as a maybe summary of what we did yesterday morning, we started by looking or doing a recap of Bayesian linear regression. Just a moment. So we did a recap of Bayesian linear regression before then diving into Gaussian processes. So what is a Gaussian process? And then we phrased the regression problem. So finding a posterior distribution on the underlying function that we are interested in as an inference problem. That requires us to look at Bayes' theorem. So Bayes' theorem contains priors, likelihoods, posteriors, and marginal likelihoods. And then in the context of Gaussian process regression, we went through all of these components in some detail. And then in the end, we looked at how to make predictions with the Gaussian process, either by sampling from the prior or also sampling from the posterior distribution, which, so both of these, when I say sampling, that requires us to make predictions at a set of test inputs. So that was yesterday, and today we want to look at some of the more intricate details of how things actually work together. So we discussed to some degree yesterday length scales or amplitude parameters, so how they influence the functions that we can model with the Gaussian process. So these are the parameters of the covariance function or the kernel. And there were also questions already yesterday that came up of along the lines of like, how do we actually set the length scale to the right value? And that is exactly what we're going to look at today. So we are looking at something called model selection. So how do we choose a good length scale, or how do we choose a good covariance function? And that all falls under the category of model selection. So we're going to start at maybe choosing good hyperparameters for a given kernel. We're going to have, so it will turn out that in order to find good hyperparameters, we're going to maximize the marginal likelihood. So the marginal likelihood from yesterday will come back to us today. We're going to have a closer look at the marginal likelihood and maybe try to understand why the marginal likelihood is meaningful as an objective to optimize when we want to find good hyperparameters. And then towards the end, we're going to look at how we choose good covariance functions. And then at the end of the lecture, we're going to look at some limitations and maybe some practical guidelines for when you work with Gaussian processes, and briefly mention a bunch of application areas. So that's kind of like what we're going to do today. So let's dive in and start with the model selection part. And I want to maybe motivate what we are actually doing here. So we already looked at linear regression 2 days ago, and we looked at training and test errors. And you saw that, you know, by optimizing or minimizing the root mean squared error on the training data, we can get a very low training error, but at some point the test error is going to take off. So we are not interested so much, at least, in the training error, but we're interested in generalization properties, so making predictions beyond the training data set. And in our case now with the Gaussian process, but also with the Bayesian in the regression setting, we get a predictive distribution. When we make predictions at some points x star, so test input x star, we predict y star, and we can now measure the generalization error by looking at the full predictive distribution. We're going to look more specifically at the log predictive density. So this is the number that's going to be shown in the top right corner, which is the log P of Y star given X star and the training data and one specific length scale. So I'm explicitly now mentioning the length scale here as well. So because this is a synthetic example, we can, so this data set that we have, so training data are these, I think the dots, and test data maybe the crosses, the green crosses. And so what we're going to measure now is the log predictive density of the predicted labels, so the Y star labels at the corresponding inputs. So for different length scales and different data sets. So now we're choosing one length scale and we're going to generate some prior samples from the Gaussian process prior. And so you've seen these kind of functions before. So these are typical functions that we would expect to get from our Gaussian process prior. So now we're going to make predictions from the posterior distribution, which you compute based on the training data here. And then we evaluate our test data or the quality of our prediction on the test data. And we're going to get this LPD value, the log predictive density of, in this case, of 0.14. And what we want to have is we want to have a log predictive density that is relatively high. So higher is better here. So I'm going to now do the same thing here. So I'm going to keep the same data set, training and test data set, but I'm going to change the length scale now. So what you can see, or what we can see now, is if we make the length scale shorter, right? So our functions look a bit more wiggly in some sense. We discussed this at relative length yesterday. And this would be the posterior predictive distribution, or the posterior Gaussian process would be indicated here on the right-hand side. And what we can see is that with the shorter length scale, we have the model becomes a bit more flexible. So also you can see this in the prior samples. So somebody said yesterday, with long length scales, we have slowly varying functions, and with shorter length scales, we then also have faster varying functions, and that gives us a bit more flexibility in terms of like what we can model. But so that's kind of like what's mentioned here. With a shorter length scale, we have a more flexible model. But what you can also see, if we compare this to the previous slide, the error bars increase much faster. So here the error bars, for example, are much higher. So the training data are these orange disks. And so if we go away from the training data with a longer length scale, the error bars they don't change really that much. It's because of the noise in the data. But if we make the length scale shorter, the error bars go up quite significantly. So with a more flexible model, we also get a faster increase in uncertainty away from the data. And then generally, this doesn't mean we have good generalization properties, but more like bad generalization properties, in the sense that we cannot really transfer much knowledge from the data that we observed to other data points. So from the training data to the test data. The shorter the length scale, if you remember what we looked at yesterday, shorter length scale means that I only need to move very little in input space for function values to become uncorrelated. And that means that the information transfer that I can do from the training data to the test data is relatively low. And that's kind of like what the last point means here. And so the log predictive density also measures this, or gives a numerical value to this. So we had in the previous, with the previous length scale, we had 0.14 as a log predictive density. Now we have 0.06, so that is lower. So this fit is actually worse than the one before. And we can go a bit more extreme and make the length scale even shorter. So you can see how super flexible these models are. And then our log predictive density is minus 0.43, so that's even worse. And now you can also see that there's pretty much no generalization, or not much generalization going on. So the error bars between the data point, even between the training data points where there are no significant gaps, they explode. and there's not much knowledge transfer going on far away from the training data. So for this particular data set, we would then say maybe the first fit is the best one. So this looks like a meaningful fit. It's a relatively simple model that explains the data. Error bars make some sense. The mean also makes sense. This one is, I think, is visibly worse. And this one looks pretty horrible. One would almost say this is overfitting. But now we can change. So if we now change the data set, so we're going to look at a different data set, and we're going to use this example with the 3 length scales that we used here. So now our training data set are these orange disks again, and our test set are these green, again, these green crosses. So now if we look at the longer length scale again, then our log predictive density is minus 1.19. And we can see that, for example, these areas down here, they are not really well covered, neither in the training set nor in the test set. So this model is actually pretty bad at predicting these values down here. If we make the length scale, and so that maybe is an indicator that the model class is not rich enough. So we may want to look at a more flexible model and want to decrease our length scale. So if we do this, so this is a shorter length scale, so the same medium-sized length scale that we had before. And now we can see that the training data is reasonably well modeled, and the predictions also make some sense. So most of the green crosses are within these shaded arrow bars. So that's a relatively good model given the training set, or given the data set that we have, and the log predictive density also indicates this. So we came from minus 1.1 to minus 0.03. So this is a much better value compared to the other one. But now we can look at an even shorter length scale, and then we get something like a fit that looks like this. So again, so the training data and the test data are definitely under, or make sense under the GP distribution. But the GP is a bit too flexible even for modeling this data. And the log predictive density indicates this again. So we would not actually choose this particular model if we just looked at the log predictive density. And we can look at maybe a third data set where now our training data are again these orange disks. And we start again with the long length scale. And we can, I think it's very clear from here that this model is pretty horrible in fitting the training set or the test set. And so the log predictive density is far in the negative. So minus 16.6 is actually a pretty bad value. So now we can decrease the length scale, so make the model class a bit richer, then it looks a bit better, but we are still missing out on data points in various regions, and not even the training data is modeled super well. But the log predictive density is significantly better, so we're now at minus 3.35. And we can then say maybe we want to increase the flexibility of the model further by decreasing the length scale. So if we do that, then we get a model that looks like this. It's not really great, but the data set is modeled significantly better, and the log predictive density also indicates that, let's say, if we had to choose between these 3 different length scales, then we would choose this short length scale for modeling this kind of data set, or for describing this kind of data set. So maybe the summary of this kind of like exercise or visualization is that we can make predictions that are equipped with uncertainty, but very clearly we also looked at like how the choice of the prior, for example, the length scales, influences the predictions we can make. And we saw that for different regression problems, so we looked at 3 different regression problems, we may require different kind of priors, so different setting of the length scale in this particular example. So the first data set, we wanted to have a relatively long length scale. In the second data set, we required a medium-sized length scale. And in the third example, we required a relatively short length scale. And so the question that we want to look at is really, how do we select a good prior? So that can go beyond the length scale parameters. Yes, there's a question.
Yeah, please, I have a question.
Yes.
Please, in relation to the explanation of the flexibility of the model,
yes,
and then against its complexity. So from what I am seeing, the more complex it becomes, the more you say it is flexible.
yes.
So how then do you differentiate this in relation to that of overfitting? Because it looks like as it becomes more flexible, it's able to fit the data very well. So what's the trade-off between that and maybe overfitting and all that?
So that's an excellent question. I would like to postpone the answer to that question to by maybe 30 minutes, because we're going to discuss this later. So we're gonna but maybe to refer a little bit back to the to linear regression. We had this example of map estimation or ridge regression, right? So we have, or maximum likelihood was only looking at data fit, because we minimize the squared error between the mean prediction or the prediction of the with a particular data set, with a particular parameter value, and the observed data points. So that was just looking at the fit of the model, right? So we looked at y minus x times theta, that norm. And that is just looking at the data fit. And then we added a regularizer, which comes from the prior distribution of the parameters. And that was penalizing the squared norm of the parameters. And that we can think of as a penalty on the model complexity. And so we will see something very similar here. It will look a bit different, but we will see this here. And we can actually assess or maybe evaluate the richness of the model through, it will turn out through the determinant of the kernel matrix. And so we will discuss this in much more detail later. So keep the question in mind. If I don't answer this at sufficient detail, please ask again, because we are actually going to discuss this later on in the lecture.
All right, thank you.
Any other questions at this point? Okay, so the question is, what kind of like, how do we select a good prior? And when we talk about priors, we're going to talk about 2 different things today. We can talk about choosing hyperparameters of the Gaussian process, which are the parameters of the kernel and maybe the parameters of the mean function. I'm going to focus only on the parameters of the kernel and maybe the likelihood, so length scale and amplitude parameter of the kernel, or periodicity parameter of the kernel, and the noise variance in the likelihood. We could also think about parameters of the mean function. And then maybe at a different level is like the question, what is actually a good kernel, or what is a good mean function? So we're going to look at these two different things in this lecture. I'm going to start with the hyperparameters. So the Gaussian process has a bunch of hyperparameters, which we can think of maybe as the parameters of the mean function, but also the parameters of the covariance function, so length scale parameters and signal variances, but also the noise variance in the likelihood. So these are we call them hyperparameters because they control the kind of like the distribution of the function, but they do not directly control the data. So they are higher level parameters. So yesterday we said we can think of in the Gaussian process setting, we can think of the function itself to be the set of parameters if we compare this with the Bayesian linear regression setting. And so these hyperparameters are higher level parameters in that sense. So when we talk about training a Gaussian process, which you may see somewhere will also come up later, it's basically about finding a good set of hyperparameters. And then we can talk about higher level model selection for mean and covariance functions. And so the automated statistician, which I mentioned yesterday, already kind of automates this in some way. Okay, so what I would like to do is now I want to just a moment. I want to maybe draw a little picture of how we can maybe think about these hyperparameters. And so we are back here. So let me maybe draw a picture of what we have up to this point. So we have some observed data. So the y values are observed values, and so I just mark this as a gray node to indicate that this is an observed value. Right, so these are observed function values. Noisy. So then we have the function itself. So that function is an unobserved quantity. So I'm just going to make this a non-gray node. So that's the unobserved function. Something we call that also latent function. And now in the Gaussian process case, we have these kind of hyperparameters, so the length scale parameters. So the length scale parameters control the distribution of the function. So we can maybe draw it in this way, that I'm going to use maybe notation like theta as the hyperparameters of the Gaussian process. So these ones are the hyperparameters of the Gaussian process. So maybe in the corresponding model for linear regression, right? So we also had observed y values, which are the functions. The noisy function values, and then we had a diagram that looked like this, which were these ones were now. So this one is the GP setting, and this one is the linear regression setting. So these are the parameters now of the model. And so what did we do on Monday to find good parameters of the model? Okay, so yes, so maximum likelihood estimation. And map estimation, yeah. Yeah, so this is all good. So okay, so somebody asked about cross-validation, so we're going to get to this later, but yes, it's possible. So we did maximum likelihood and map estimation, and in the Bayesian linear regression setting, we were putting a prior distribution on these parameters, and then we were integrating them out. But effectively, we were trying to, if we look at only maximum likelihood and map estimation, we basically maximized P of y given theta. I'm ignoring all the input values, the x values here. They are currently, they're just disturbing in terms of notation. So we were looking at, so that one would be maximizing the likelihood, or we would look at maximizing P of y given theta times P of theta, which would be maximizing the posterior distribution. So now, how are we doing the same or similar things with the Gaussian process? Any suggestions? So we could sample functions, but if we what do you want to do with sampled functions? So we can generate function samples, okay? But what do you want to do with the sampled functions? So in practice, we don't have labeled test data, so we cannot evaluate the generalization performance directly. Is there a way of like maybe using the same ideas that we used here to find good parameters to find good hyperparameters in the Gaussian process?
I think you can also maximize uh, the, the marginal likelihood.
Okay, so I mean, we're going to get there in the end. The question is, how do we come to the conclusion that we want to maximize the marginal likelihood?
Okay, since the prior depend on the parameter theta and the posteriori also, so we can find a parameter that maximize both the prior and the posterior.
Okay, so
Hello.
hello.
Yes, because you say that once we have a good, a better, higher our log predictive density, better our model, and the log predictive density depend of the length scale. So
That's right.
they can just decide to use either the maximum likelihood in order to find the best length scale, or using the map to find the best length scale.
So this would be a really good idea to look at the log predictive density if we had labeled test data. So that's what we had in the motivating example before, where we had the Y star values, the green crosses. Then we could just compare the log predictive densities, and then we can choose the length scale that gives us a better number. So it's a good idea. But in practice, we only have training data available. So the maximum likelihood and the map estimation, they only require training data. Ideally, we would use exactly what you said, like the evaluation of the model on the test data, but we don't have labeled test data available at the time of training, maybe even ever. So maybe an idea is like, why don't we try to write down the exactly the same equations here on the left-hand side. So why don't we try to find the argmax of P of y given theta. So now theta are the hyperparameters in the GP setting. But so if we had a direct connection, let's say, which looked like this, without this kind of like stuff in the middle, then we would do maximum likelihood estimation. But we don't have that that direct connection from the hyperparameters to the data. So now we have to modify or actually write down how we get to this particular equation. Any suggestions?
Please.
Yes?
Yes, I think since the y, there's a relationship between the y and the f. They can just, I mean, they can just like change the expression of y by f plus a random noise. I don't know, something like.
Okay, so you're correctly saying that we need to get f involved somehow. And so
Yeah, yes.
y and f are connected directly, and so theta and f are also connected directly. So so we're just going to maybe try to rewrite this particular equation in a slightly different form. So we can maybe write the same thing as P of y comma f given theta, and we integrate out df. Right, so that's a marginalization that we do. So here we have a joint distribution between y and f, and we integrate out f, and then we end up with exactly P of y given theta. Yeah, so similar to, maybe use a different color. P of a is the integral of P of a comma b db. So that's kind of like the marginalization property or marginalization rule that we just used, or sum rule. So that is used down here. So this is with the sum rule. And now we can rewrite this joint distribution P of y given f in a slightly different way, because so we can now use the structure of this graphical model. And we know that in the directed graphical model, each directed arrow is a conditional distribution. So we can now write this as the integral of P of y given f, which would be this arrow here, times P of f given theta, which is this arrow, df. So that would be exactly the same. Yeah, I'm just going to write down. This is again P of y given theta. Yeah, so we exploit the relationship between theta and f and y to write down the P of y given theta distribution in this way. So now the question is, does this look familiar?
Yes, it does.
What is it?
So it currently looks like the marginal likelihood that we can derive from a Bayes theorem.
Mm-hmm. That's right. So this is the marginal likelihood. And so that is exactly right. And we came to the marginal likelihood now through a completely different way, where we effectively wanted to do maximum likelihood estimation on the hyperparameters given the data. So it turns out that the marginal likelihood is the objective function if we wanted to do some sort of like some form of maximum likelihood estimation on the hyperparameters. And so it's not exactly a maximum likelihood because the likelihood would only be this term here. So that is the likelihood. I need to work on my handwriting, sorry. This term is the likelihood. But in order to get the theta parameters in, we also need to look at the prior distribution. So this is the GP prior. And previously, we never conditioned on the theta parameters, but they were implicitly always there because we always use a kernel or a covariance function and a mean function. But they would have been very misleading in the equations that we had before. But the GP prior is always conditioned on the, for example, the length scale parameters. So now maximizing the marginal likelihood. So given that we really wanted to come from over here, from the maximum likelihood estimation to, right, so the equation is exactly the same, but it's not quite maximum likelihood. So maximizing the marginal likelihood is also called, I mean, because it's very similar to maximum likelihood, it's also called maximum likelihood type 2 estimation. So it's also called maximum likelihood type 2 because it requires the second level of inference here as well. So that's one thing we can do, and we're going to do this a lot later. Now the other question that we had was what happens if we actually now look at map estimation in the linear regression setting? How does that now translate into kind of like map estimation in some form in the Gaussian process setting? So what do we require in map estimation for in linear regression? What did we do?
So in the case of linear regression, we require the prior on the parameter.
Exactly. So we require a prior distribution on theta. And we can do exactly the same thing in the, and base theorem, then we use base theorem to get there, exactly. Prior on theta plus base theorem will then allow us to derive the map estimator. And so that's exactly the approach that we would also take in the Gaussian process when we can place a prior distribution on the hyperparameters, for example, the length scale parameters, and then use base theorem to compute the posterior distribution. And that's what we're going to do right now. All right, so this kind of slide summarizes a little bit of what we wrote down a few minutes ago. So we have the y values over here, these observed values. We have the f value here, and then I'm just splitting up the hyperparameters that we are looking at for the time being. So we have psi parameters, which are the length scale and the amplitude, for example, and I explicitly put in the signal variance, the noise variance, as well as an additional hyperparameter. And we're just going to summarize both of these things in the theta parameter. So, and now, as you said before, we are now placing a prior distribution on the set of hyperparameters here. And then we can find the posterior distribution, which is this blue distribution. So P of theta given x and y. We use Bayes' theorem here. It's P of theta times P of y given x and theta divided by P of y given x. And so, and you already realize or see that the orange block here is exactly the marginal likelihood that we computed yesterday. So it's P of y given f and f of x basically times P of f given theta. So that orange block is the same marginal likelihood that we looked at yesterday. And this is what it, again, so I'm just going to copy this posterior distribution over from the previous slide. So the marginal likelihood in this orange block here is the integral of the likelihood evaluated at the training set times the prior distribution evaluated at the training set. And now I'm explicitly conditioning the prior distribution on the theta parameters, on the length scale and amplitude parameters. So now if we want to maximize the posterior distribution on the hyperparameters, then it is sufficient to, or it's equivalent to maximizing the log posterior distribution with respect to the hyperparameters, and that would require us to maximize the numerator of this expression. So the log prior plus the log marginal likelihood. So that is this expression down here. And if we now choose a uniform prior on the theta parameters, then P of theta would be constant everywhere. Then maximizing the posterior distribution would be equivalent to maximizing the marginal likelihood. And that is something similar that we also had in linear regression, where we said that the maximum likelihood estimator and the map estimator are identical if we had a uniform prior distribution on the parameters. So then these things are identical. Or if you make the variance of the Gaussian prior, if that tends to infinity, maybe that's kind of like what we said. And that would be equivalent to a uniform prior that has probability mass everywhere, equal probability mass. Yes, please, there's a question.
Hello, Mark. I would like to clarify something.
Mm-hmm.
We're talking about marginal likelihood from the formula given on the first line. Are you saying the marginal likelihood is P of y, s given theta, or it's the one in the denominator, P of y given x? Because I
so that's a okay. So that is actually a very good question. I'm saying in this setting here, the marginal likelihood is this orange block. But you're correct. So this P of y given x also looks like a marginal likelihood, or some sort of like marginalized likelihood in a different way. And let me try to write this down, what this actually means. So just a second, need to switch again. So we're going to look at this term here, correct? So P of y given x is the integral of P of y given x and theta times P of theta d theta. So this is also some form of marginalization, but this term here is still the marginal likelihood. So sometimes people also call it the marginalized likelihood, and maybe that is a better expression, sorry, because it's clearer what it means. Marginalized likelihood. So marginalize means integrate out. And so the marginalized likelihood we get if we integrate out the likelihood, and this term here is the likelihood. And this is what we have in our integral. So in that sense, what we integrate out here is already the marginal likelihood. So, and maybe in this case, so this is a double marginalization, right? So it's the marginalized marginal likelihood. So it's a kind of marginal likelihood, but it's like it requires to solve two integrals. Yeah, we can maybe spell this out more explicitly. So that term here is the marginal likelihood. And then we have this additional integral that sits on top. So the marginal likelihood is also called the evidence. So same thing. It's just a different word for this. But the this kind of like marginalized marginal likelihood, so this term here is not called the evidence. Does that clarify things a little bit more?
Sorry, which term do you say does not represent evidence?
So the marginal likelihood is also called the evidence. So the orange block is also called evidence.
All right.
Mm-hmm. So then there's also a question about like what the role of theta is. So previously we said theta are the parameters of the linear regression model. So now these parameters turn into hyperparameters now, and so that something turns into a hyperparameter if you basically if you add an additional latent variable or unobserved quantity between the previous parameters and your observed data. So parameters are normally the first level of unobserved quantities, and then you have hyperparameters which are at the second level of unobserved quantities. So if you call this maybe your level 1, and this is level 2. And here we only have level 1. There's no level 2. If so, maybe one thing to think about. So like if we were to place a specific prior in the linear regression setting, if we were to place, for example, a Gaussian prior on theta, and we wanted to learn, for example, M0 and S0, then they would play the role of the hyperparameters as well. So that would be a level. So if we actually wanted to learn the parameters of the prior distribution instead of setting them, then we could do the same kind of thing in linear regression, but we didn't do this. Does that make more sense now, or is it more confusing? Okay. So then let me go back here. So this is the setting that we had. So we we found like a correspondence between maximizing the likelihood in the linear regression setting with maximizing the marginal likelihood in the Gaussian process setting. And so what I also mentioned earlier, so this is also called maximum likelihood type 2 because there is this close correspondence between maximum likelihood and marginal likelihood optimization, but just at a different level. So the spirit is the same thing. The equation that we optimize is the same thing, but there's a very important difference by optimizing the marginal likelihood, and the properties of the marginal likelihood will be super critical later on when we come to regularization and stuff like this, because unlike the maximum likelihood estimator, which tends to overfitting because it only looks at the training error, the marginal likelihood has an automatic regularization term in there. So again, I'm just going to write down what the marginal likelihood is, and we already talked about this at length yesterday. The marginal likelihood in the Gaussian process is actually easy to compute. It turns out to be just a number, and I'm just going to write this down as a kind of functional relationship here. So this is actually not a probability distribution, but just a real number because the y values are observed. If we now maximize we can now learn the Gaussian process hyperparameters by maximizing the log marginal likelihood. And so the log marginal likelihood is given by this expression here. So we had that expression yesterday already. So there is the minus a half y transpose k inverse times y. So just defining this k theta as k plus sigma n squared times I, minus half log determinant of k theta plus constant. And I'm having the subscript theta on the k because that's the only place where the hyperparameters show up, which are in these k theta terms. So now the next question is how do we maximize or optimize the marginal likelihood? How do we solve optimization problems? Suggestions?
You differentiate with respect to the parameter and set it equals to 0.
Yep. Okay, so we want to compute the derivative and set the derivative to 0. And that is exactly what is happening here. What we normally do is we compute the partial derivatives of the log marginal likelihood with respect to the individual hyperparameters and set it to 0. So the derivative is given here. I mean, the derivation it's going to take a little bit, but I just wanted to write down the equations for you so you don't have to worry too much about it. And do you, so when you say set it to 0, do you think you can solve for theta directly and say theta equals, something that is similar to a maximum likelihood estimator where we wrote down, was it theta is x transpose x inverse times x transpose y? Do you think we can do the same thing here where we write down optimal theta parameters are the following?
I think it's going to be a different case in this case because unlike trying to constrain to some values in the previous cases, we might easily be updating the parameters rather than just setting stuff to 0 at this point.
Yeah. So finding a closed form solution is not possible here, but we can use gradient descent to find at least local optima of the marginal likelihood. So there's no closed form solution, but we can use gradient descent for finding the good values.
Sorry, I have a question.
Mm-hmm.
The hyperparameters, do you choose which hyperparameters to differentiate over, or
all possible hyperparameters.
So you differentiate with respect to all hyperparameters. So that means you compute a Jacobian or like a gradient of the log marginal likelihood with respect to, for example, the length scale parameter, the noise variance, the signal amplitude, maybe a periodicity parameter. So all parameters that parameterize your kernel function or mean function, they would show up here. So you can optimize all of them.
Okay. Okay.
Okay, so I recommend let's have maybe a 10 minutes break, and then I'm going to show you some pictures of like how things work. And so I think that I think now is a good time for a break, because the maybe illustration will take a little bit longer. So let's come back at say 10 past, so that's 12 minutes from now, and then we continue with some illustration. And please, somebody remind me that I continue recording after the break. Okay, welcome back, everyone. So references to the, what do you mean? So can we have the references to the differentiation of the parameters? What do you mean by references?
I'm talking with respect to the gradient bit of optimization to get the hyperparameters, how it was derived. Like, can we get any paper or book to it? Like, it seems, I don't know whether the steps have been truncated in terms of like its the derivation. I don't know.
So effectively the equations, let's say if you look at the log marginal likelihood up here, the derivative of the first term, so it's the chain rule. So you have to take the derivative of the K inverse matrix. So that is minus K inverse times the derivative of K with respect to theta. So that's the first term, times K inverse. So that is by definition of like how you compute derivatives of inverses. And then you need to look up in the matrix cookbook how to compute the derivative or log determinant. And then you would get the second term. So this is pretty much straight out of a book, where you look up how to compute the derivative of an inverse matrix and to how to compute the derivative of a log determinant term. So these are straight direct equations from any book on matrix or on derivatives. Okay, thanks. So I'm recording again, so thanks for the reminder. So now, given that we have now looked at this, at the kind of like the maths and the derivation of how to optimize hyperparameters, let's see what happens here. So we're going to look at this kind of example where our training data is given by these blue crosses, and we have initialized our Gaussian process to some length scale, some noise, and some signal variance, so the amplitude parameter. And now we're going to run gradient descent on the log marginal likelihood. And so we're going to look at the first term over here, so y transpose k inverse times y, which is going to be we're going to call this the data fit term, and I'm going to explain on the next slide why that is the case. And the number which is behind elbow is the log marginal likelihood. So what we would expect is that the log marginal likelihood gets better as we now run gradient descent on our hyperparameters. And then you can also see what the posterior Gaussian process looks like. So at the moment, with this particular initialization of the hyperparameters, the posterior mean is the orange line, and the posterior uncertainty is indicated by these shaded arrow bars or shaded regions. So now let's run gradient descent on this. You can see that the log marginal likelihood gets better, so it gets higher. And so this fit looks pretty good already. But you can also see now the data fit term gets worse. All right, so the data fit, oh, sorry, no, sorry, I take this back. The data fit penalty that the data fit term gets worse, so we want to have higher data fit. But overall, the marginal likelihood term increases. So initially, with our very short length scale, we can model the data extremely well. So the data fit term is very high. But the marginal likelihood value is really bad in the beginning. So we need to make a compromise between fitting the data and getting good marginal likelihood values. And we want to now have a look why that is the case. So the fit in the end also looks much more meaningful than before. So this one in the beginning, if you look at this, it looks a little bit like overfitting, right? So at least the posterior mean nicely hits the data. The posterior mean is overfitting. But the marginal likelihood values are not ideal. And if we run gradient descent, we would get a fit that looks significantly different and much better, actually, also in terms of like generalization properties. And so now the question is, why is this? And we're going to look at the marginal likelihood at, we're just going to and see what kind of properties the marginal likelihood actually has. So we're copying from previous slide the marginal likelihood term, and I'm highlighting two particular terms over here. The first one, this is a quadratic term, is we call earlier as the data fit term, and this term measures whether an observation y training observation y is within the variation allowed by the prior distribution. So effectively, that measures whether we can model the data. The second term is the determinant, and if you think of this, the determinant is the product of the variances of the prior, and therefore it also computes the volume of the prior. If you now think of maybe a volume as the richness of the model class, then we can take this term as a penalty on the model complexity. And that kind of like ties back to the question that we had early on. What do we mean by like model complexity? How do we measure this? So this term in the marginal likelihood is exactly this penalty term on the model complexity class, this log determinant term. So if we want to maximize now the log marginal likelihood, so maximizing the first term means to bring this term to as close to 0 as possible. So because the y transpose k inverse times y, that term is non-negative, we have a minus in front of this, so this will always be smaller than 0 or smaller equal than 0. And so getting this as close to 0 as possible is the idea. And then the other term here is it's kind of like this log determinant term, which we subtract from this term. So this, again, so the log determinant term ideally goes to something that is negative, or so we want to make the volume of k as small as possible. And that normally means we restrict the model class to something that is relatively simple. So what that means is that the marginal likelihood kind of like automatically trades off between fitting the data, which is this quadratic term, and taking care of the model complexity, which is this log determinant term. Yeah, so if we think back to ridge regression or map estimation, we had this the prior penalty, the penalty on the parameters, on the amplitude of the parameters, so the norm of the parameters, that would correspond to the model complexity term. The data fit term is the same that came from the likelihood, and the model complexity term could be interpreted by the penalty on the amplitude of the prior could be or can be interpreted as the complexity of the model. So the more flexibility we give the parameters, the range of the parameters, the more flexible the model. And in the similar way, we can interpret this log determinant term. So I also want to have a brief look at the marginal likelihood surface. So the marginal likelihood surface, so this is the marginal likelihood surface on 2 dimensions, where we have the noise value on the horizontal axis, the length scale on the vertical axis for a given data set. And what we see here, I mean, it's a bit difficult to see, but maybe on the web, it's a bit easier to see. We have 3 local optima here. And so that means, in the first place, the marginal likelihood may give us different answers depending on where we start our optimization. But I was now wondering whether you could give me some idea of what kind of models you would expect in these cases. So what would the functions or the posterior, what would the Gaussian process look like if we were to choose this particular noise value and this particular length scale? And I can tell you that the data lies between +5 and -5. Yeah, so data is between +5 and -5. So if we choose a length scale that is, let's say, 4 of, it's on a logarithmic scale. So let's say length scale ballpark, maybe 10. What would that mean? Length scale 10 and a relatively high noise value. What would that mean for the Gaussian process?
Okay, so for that one, because the length scale is high, so I will expect something that will not vary too much, but to still have a high amplitude because of the noise value.
Yeah, okay, so that's an excellent start. So we have very long length scales. So we have a function or a GP that doesn't really change much, and then we have a lot of noise, which would mean you say we have a lot of variance. Yeah, so that's correct. So we have a lot of, effectively what it means is that the structure of the data is oh yeah, you can draw in here. Somebody just was drawing a function or drawing something in here. You can draw on the screen if you want to. Nobody wants to draw pictures. So you say there's something that varies maybe very slowly. Is that kind of like, that's what you said, right? So now we have a lot of uncertainty, which means that basically, if these are the uncertainty bars, then we would, if the data was actually lying, looking like this, then we would effectively model the signal in the data, or we completely ignore the signal in the data and just treat everything as noise.
So that, Mark,
yes.
The noise, yeah, is it the signal noise or the other noise? We have 2 noise parameters. Right?
So okay, so that's a it's a good question, and so I'm going to ignore the amplitude of the function for the time being. So what we actually did is we were optimizing the amplitude of the function for every single grid point in here. So it's for every combination of noise and length scale, we have an optimal amplitude, but let's just ignore the amplitude for the time being. So that's kind of like what things look like.
Okay, okay.
Okay, so maybe the now let's have a look at a different example, maybe the one down here. So this one here. So assuming our data looks like this, what would the corresponding function look like? So we have relatively little noise, we have a relatively short length scale. What do you think the corresponding function could look like, or the GP would look like?
We're going to have a more flexible for a GP.
So we have more complexity or more flexibility. Yes, so that is correct, because the length scale is short, right? So what would you expect the GP to look like here?
It's going to oscillate.
Do you want to draw a picture, draw on the screen? Okay, can you do this, or otherwise I'll draw for you as you describe it.
Where can I do it?
So there's at the bottom, there is or there's some option to draw on the screen.
Okay.
Yeah, yeah.
Oh, man. I'm repeating. Yeah, I didn't do
Yeah, yeah. Yeah, okay, so that looks promising. And there's very little noise, right? Oh yeah. So oh yeah, so somebody is asking, okay, can you explain what the diagram means? So sorry about this. The dark blue colors are values of high marginal likelihood, and the yellow colors are very low values of marginal likelihood. So if we find a peak in the dark blue, that means that there is a good explanation of the data according to the marginal likelihood, and yellow is pretty horrible. So okay, so this here at the bottom is an explanation of the of this particular configuration of noise and length scale. If we, okay, ignoring all the variances, but this is kind of like what the posterior mean could look like. And so what happens here at the bottom right? What happens here? What is the corresponding value, or what would a function look like if we again were to draw some function values here? What could the function look like? So in the top right, we have long length scale, high noise, bottom left, short length scale, and very little noise. And now here we are in kind of like a regime where we still have actually quite a lot of noise, but the length scale is a bit shorter. So what could it look like? Any suggestions?
I want to try, honestly.
Say again?
I want to try. So since we have a shorter length scale, so and not too short, so I expect that it will be a little bit smooth, but we have a large variance. So I have variance, so I will be expecting smoothness, but still having a larger. So the error bars will still be a little bit large, something like that.
Okay, so that also looks good, and we still have a lot of noise in here as well. Okay, cool. So let's have a okay, so the people who were drawing here, could you please erase this again, because it's going to show up on the next slide again. I can't get rid of this myself. Yeah. Okay. So the explanations of what we had is actually, so they are very good. So we had the one example here in the top is a very long length scale, and everything or much of this is modeled with noise. And if you look at the log marginal likelihood value, it's minus 1.28 or minus 1.23, minus 1.3. Here at the bottom right, we have still a lot of noise, but the length scale is a bit shorter, so you can see that the function varies a little bit faster. The marginal likelihood value is a little bit better than up here. And here at the bottom left, we have very low noise and a lot of and a very short length scale. The function can vary relatively quickly, and so the fit is really good. So the marginal likelihood value here is minus 1.22. So according to this data set, the bottom left fit would be the best, but you can see that the marginal likelihood values are actually relatively similar. So we would find 3 different explanations of the data that kind of makes sense. And here's a 4th example where we just have a value here in this yellow area, which I said earlier, this is pretty bad. And it's really bad because the data is not really explained by the Gaussian process. So even if the length scale is maybe okay, the uncertainty is not high enough to explain the data. And so the marginal likelihood also expresses this by a really high negative value and say this is a really bad place to be. So, and maybe just if you want to go, if you want to go to this website, which I sent around yesterday, you can play around with this kind of diagram a little bit more. So let me just try to find the website here. So you can see the screen share. And so here we have this kind of the surface plot of the marginal likelihood, and we modified the colors a little bit so it's a bit easier to see. And you can click within this range, and you can see the corresponding fit here on the left-hand side. And you can really play around with what the corresponding fits would look like if you were to be, let's say, totally extreme. For example, you choose a very short length scale and with very high a very low noise. So then this would be pretty bad. Long length scale with high noise. So all of this you can play around with. So it's, I hope it's useful. We hope it's useful. And there's actually a lot of other stuff that you can play around with. Yeah, again, like modifying length scales, what that means. All right. So that is where this plot comes from. So the website is here again. So if you want to have a look at this, then will be all fine. So to maybe summarize bits and pieces that we have seen here is that the marginal likelihood is non-convex, right? So we have like theoretically multiple optima, local optima. And especially in the small data regime, the GP can end up in about 3 different situations when we optimize the hyperparameters. And maybe some of these 3 are kind of like reflected in the marginal likelihood plot that we saw earlier. So either we end up with short length scales and low noise, so we have a highly nonlinear mean function with little noise around it. Long length scale with high noise, where we effectively treat the signal to be just noise. So there's no real signal in the data, but most of what we see is considered to be noise. And some sort of like hybrid where we have maybe shorter length scales and a bit of noise, which kind of like interpolates between these 2 extremes. But and because of this, it's worthwhile restarting the hyperparameter optimization from random initializations to kind of like find the best expression or the best value of the marginal likelihood. But if you look actually at the marginal likelihood surface as a function of the data set size, so if you increase the data set size, then maybe 2 of these local optima disappear, and you end up with with 1 explanation of the data. So the more data you have, the more peaked the posterior distribution over the hyperparameters is, or the more unique the optimum of the marginal likelihood surface. So then, you know, we could maybe think about integrating out the hyperparameters as well. Because instead of like what we did in Bayesian linear regression, at some point said, okay, let's just not optimize the hyperparameters. Let's just integrate them out. We place a prior on them, and then we integrated them out. So that was Bayesian linear regression. The problem here is that we can't do this anymore. We have no closed form solution. And we could do this approximately, for example, by using Markov chain Monte Carlo sampling, but that is relatively expensive. And maybe worthwhile doing this in the low data regime where we have multiple different optima. We kind of like want to take everything into account. But if in the high data regime, it's probably not worthwhile because the posterior is hyperparameter posterior is relatively peaked, and then we can just use a point estimate. So that's fine. In a low data regime, it would make sense to integrate them out, but it's a bit complicated and computationally heavy. So I also wanted to maybe recap a little bit on a bit more on like why the marginal likelihood seems to be working. So starting from like early on today, we were talking about generalization performance on unseen test data. So we looked at the log predictive density, and we at test data to motivate using some sort of like model selection. But the marginal likelihood doesn't actually know anything about test data, but it seems to be working relatively fine. So we also saw on Monday that just looking at the training error is not a good idea. So because we end up in overfitting situations if we do a maximum likelihood. If we just add uncertainty to our predictions, that also doesn't really help if the model is wrong. But so maybe an example of this, what I mean is, looks maybe like this, right? So we add uncertainty to our predictions. The model is wrong in the sense that the hyperparameters don't make much sense, but just adding uncertainty, we don't get good generalization performance. We just add a lot of uncertainty to our predictions, right? So the kind of like knowledge transfer from, or information transfer from the training data to test data is very low here. But if we make a prediction, let's say maybe at minus 3.5 or even -3, we would just say, I have no idea what's going on. So adding uncertainty by itself doesn't really help if the model is completely wrong. But what it does is it makes our predictions more cautious by saying, well, I don't actually know what's happening. So that is what adding uncertainty does. And the marginal likelihood seems to find a relatively good balance between fitting the data and finding a simple model. And therefore, it kind of like implements as a practical implementation of Occam's razor. Have you heard of Occam's razor in previous courses? Yes. Okay. So what does Occam's razor say? Oh, with Usman, great. So what does Occam's razor say?
Occam's razor is an assumption that the simplest model works best.
Mm-hmm. Yeah. So that, I think that's a good way of describing it. Right. So if you, I think maybe in maybe slightly different words, Occam's razor says, if you have multiple explanations of your data, choose the one that is the simplest. And that is, or choose the simplest model that explains your data. So various different versions or different words of kind of explaining what Occam's razor means. And that is exactly the trade-off between fitting the data and finding a simple model. And now what I want to look at now is I want to find out why the marginal likelihood leads to models that generalize well. So we already saw there is this kind of like trade-off between data fit and model complexity in the marginal likelihood term. But I maybe also want to give another look at or perspective on the marginal likelihood as a predictive model. So, and more specifically, I want to look at the equation of the marginal likelihood. So we can, so this is the marginal likelihood. I'm ignoring the x values here. But what I want to do is, what this equation says is, it's the probability density function of the training targets given the parameters, or hyperparameters in this case. So, and let me just switch again to the other device, so I can derive this more easily. So we can write the marginal likelihood. So this is the marginal likelihood. And so this vector y is just a collection of n different values, n different training observations. And we can, what we can do now is we can factorize this. And so we can write this as, if you remember from one of your introductory courses, I can write a joint distribution P of A comma B as P of A given B times P of B. Yeah, you remember that from one of your introductory courses? Okay, cool. So we're going to do the same thing here. So we're going to write this as P of Y1 times P of Y2 given Y1. So this is P of Y1 comma Y2, so that's a joint distribution here, times P of Y3 given Y2, let me just maybe write it a different way, Y1 comma Y2. So now this one would be now the joint distribution of PY1 comma Y2 comma Y3. And then we can continue like this. So just keep multiplying things together up to P of yn given y1 up to yn minus 1. Does this this factorization is that clear?
Yes, but where's the parameter?
Oh yeah, sorry, I keep forgetting the parameters. Yes, thanks for that. Py1 given theta given comma theta given theta, and that one would also be given theta. Yeah, so that's correct. So sorry about that. Factorization otherwise makes sense. Okay, so that's kind of like what I wrote down here as well. So same thing that we just did, and we can summarize this or write this in a more slightly more compact form, where we just start with P of y1 given theta, and then we have a product of P of yn given all previous n's also conditioned on theta. So by looking at this expression, so we're just going to copy this over from the previous slides, exactly the same thing, the factorization that we had before. We can think of this as a sequence model, right? So where data arrives sequentially. We start with P of y1, and then once P of y1 has arrived, maybe P of y2 comes next, and so on and so forth. If we think of this as a sequence model, then we can think of the marginal likelihood to be composed of sequential predictions. And it predicts the, let's say, the nth training observation given all previous observations, so y1 to yn minus 1, and keeps multiplying things together. And if you then think of this as predicting the training data yn that has not been accounted for, so it is not in our training set yet, we make a prediction because we only condition on the previous data to predict the next data point, then we effectively treat the next data point as some sort of like test data point, an unobserved quantity, and then we observe it, and then we can condition on it as well. So the intuition now behind this is that if the marginal likelihood continuously predicts well on all n previous points or training data set, it will probably also do a prediction the next time, a good prediction the next time that happens. So, and that's maybe, we can think of this therefore as a proxy for the generalization error on some unseen test data. So that's how we can maybe interpret the marginal likelihood as a proxy for the generalization error on some unseen test data, or maybe the quality of the prediction on some unseen test data, because the marginal likelihood already does this kind of sequential prediction implicitly. And so I want to show you like an example of like how this works. So you have, so again, we have this factorization down here of the marginal likelihood. What I'm going to show you here now is a GP prior, or whatever, is a GP conditioned on the training data that we have already observed with fixed length scale, fixed hyperparameters. Now we're going to see observations which are indicated by these red crosses, and the predictive uncertainty is, or 2 times the standard deviation, is indicated by this orange bar. So what we're going to see here now is that the log predictive distribution or density, that's the values that we had earlier, at y1, when we evaluate this orange bar at this red cross, is minus 1.7. And what we're going to see here in the second row is the predictive distribution of the current observation given all previous observations. So this empty set will disappear in a moment and will be replaced by observations that we already have in our training set. So if we continue, so if we do this now sequentially, we're going to get something that looks like this, right? So you can see the GP changing. So this upper value is the quality of the individual prediction. And if we sum all of these values up that we have observed, then we get to the value here at the bottom, which is the log marginal likelihood value. So we can do this maybe again, right? So we start here. And normally, if the values are within, I think within a good range of the orange bar, then the predictive quality is good. If the red cross is outside the bar, you will see that this the value gets some sort of like a hit. So let's have a. Unfortunately, I don't have tools to actually stop the animation, but you can see if you compare these values up here, then some of these values, so there was a -5 something, that was a value that was pretty bad because the red cross was outside or far outside even the orange bar. And so there's also a value -12. If you look at this, that you will identify this because the red cross is far outside the orange bar. Should come soon. There we go. Yeah, so that value was a very bad predictive value, or had a predictive log likelihood. So that's kind of like what the marginal likelihood does. And we can do the same thing again with shorter length scales, longer length scale. Now we can look at the marginal likelihood again as a way of like doing things, and we do exactly the same thing here. We now go from the left to the right and do a predictive distribution of our training data, or the next training data point conditioned on all previous training data points. And now we see how the log marginal likelihood evolves over time, and the log predictive density of this test point, this training point, given the previous test points, is shown here. We just keep summing them up. And we can see that there's pretty much no generalization happening because the length scale is very short. But the marginal likelihood does effectively this sequential prediction here, and sums these predictions up. So if we were now to increase the length scale, and make it a very long length scale, then this is what happens. So now we have a slowly varying function with a very long length scale. And we can see also now the marginal likelihood has problems predicting what the next real training point is given the previous data points. And so we get a lot of penalties for not being able to model the data. And so we can now find so we can optimize the marginal likelihood, kind of like run these sequential predictions, and then find the optimal length scale. And if we do that, then the marginal likelihood predictions would look like this, these sequential predictions. And we can see that the training data is relatively well predicted. There's still some noise available here, but yeah. So this kind of like fit looks much more sensible than any of the other fits that we had earlier. So that's the marginal likelihood, how the marginal likelihood can be interpreted as a sequential prediction model on the training data set. So if we now, if we look at these kind of like 3 examples that we had here with short length scale, long length scale, and optimal length scale, and see what the marginal likelihood values look like as a function of the number of data points that we add. So in the beginning, the marginal likelihood values kind of like agree with in all of these three settings. And then we can see that the long length scale marginal likelihood value really plummets. So that's a really bad sign. And the short length scale will also go down, or say will be significantly different from the optimal length scale. So if we, right, so even from the sequential prediction, we would find the optimal length scale also very clearly if we look at the trace plot of the marginal likelihood values if we do these kind of sequential predictions. So the problem with the short length scale is that it consistently overestimates the variance. Yeah. So if we go back to this example here, right? So it's effectively just adding a lot of noise everywhere, and it needs to do this, but there is no generalization going on. And so, and because there's a lot of noise, there's no high density, right? So when we talk about high density, we normally think that the predictive distribution is relatively concentrated. But here we just have a lot of uncertainty everywhere. So the long length scale consistently underestimates the variances. And most of the observations are outside the error bars. And that is, that's a big problem as well, because then we cannot explain the data. And if we choose the optimal length scale, then that one trades off both behaviors reasonably well. And that is, maybe we can also now tie this back to the explanation that we had earlier of like fitting the data and having relatively low model complexity. It's a question. Okay, so the question is, how is the parameter that maximizes the marginal likelihood the lower bound of the likelihood? So what I mentioned here is the values that I showed earlier in some of the plots said elbow in them. Not sure where that was, but in this particular case, it wasn't the elbow, it was actually the marginal likelihood. The elbow, so elbow ELBO stands for evidence lower bound. So you may have seen this in, it comes from variational inference, but you probably have seen this in the variational autoencoder somewhere. The evidence lower bound is a lower bound on the marginal likelihood or log marginal likelihood. So in cases where you cannot compute the marginal likelihood, you can often lower bound the marginal likelihood and then find an approximation to the marginal likelihood. The marginal likelihood is a thing that you actually want to have. And in some cases, you can't compute it, and then you can find a lower bound on this, which is called the evidence lower bound. So we already know that the marginal likelihood is also called the evidence, and the evidence lower bound is the elbow that you find in variational inference or the variational autoencoder. Does that answer your question to some reasonable degree? Yeah, so but keep in mind, so the elbow is not a lower bound of the likelihood, it's a lower bound of the marginal likelihood. Okay. So, okay. I think now is maybe a good time for having a break, and then we can maybe come or finish the lecture in the third part of today. So my suggestion is we come back at 10 past, and then we're going to go through the last bit of today's lecture and finish the Gaussian processes. Okay, welcome back, everyone. So in the last part for today's lecture, I would like to start maybe looking at different kinds of model selection. So at the moment or up to now, we only spoke about hyperparameters, optimizing hyperparameters, but we also need to think about how to choose a good mean function or a good kernels or a covariance function. So now the question is like, how do we find the best kernel, the best mean function? And we have multiple options here at hand. So one of them is to do cross-validation. So somebody already mentioned this earlier as an option for finding length scales. So that is the same option. So you could find length scales by doing cross-validation. It's pretty expensive in some sense. So the marginal likelihood optimization is actually a bit better compute-wise. But we can do the same here for kernels as well. We can think about using Bayesian information criterion or archaic information criteria, which which other people use for non-probabilistic models. But we can also use the marginal likelihood again as a way to compare the quality of kernels and mean functions. And the reasoning comes exactly from the same place where that we used earlier from hyperparameters. We can think of the marginal likelihood as a way to sequentially predict the data set, and instead of like changing only the hyperparameters, we can also change the kernel or the mean function. And so that's exactly what we're gonna do now. So we're going to go look at a very simple example. So we are looking at a data set with 8 data points. So these 8 data points here. We're choosing a mean function, so prior mean function to be identical to 0, so that doesn't bother us too much. We use the map hyperparameters for each kernel, or think of this as the maximum marginal likelihood hyperparameters for each kernel. So we train the hyperparameters in the way that we normally do, that we also discussed earlier. And then we're going to look at the log marginal likelihood values for each optimized model. And so optimized model in this case means we're looking at 4 different kernels. So if we use a constant kernel, so that is a kernel that allows us to just add a bias to the data, bias to the function that we want to model. So then we would get a posterior Gaussian process, which looks like this, and that is the optimal bias that we can find, and we would get a log marginal likelihood value of -1.1. So now we can use a linear kernel, so which makes the assumption that the data can be modeled with a straight line. So that is pretty much exactly the same thing that we do in linear regression without features, where we just add, but with a bias term. And here we would get a slightly better log marginal likelihood value, which is -1. We could use a Matern kernel. So that's a kernel that we discussed yesterday a little bit, which allows us to model things in a more flexible way. So we use a kernel where we make the underlying assumption, where we make the assumption that the underlying function is 2 or 3 times differentiable. And then we would get a fit that looks like this. And that looks much more meaningful, looks much more meaningful than just having a linear kernel or a constant kernel where we pretty much say everything is noise. So here we actually have some structure in the model. So here we have a value of -0.86. And if we use the Gaussian kernel or the squared exponential kernel, we get a log marginal likelihood value of about -0.7. So if we just compare the log marginal likelihood values, then we would choose this particular kernel as the correct kernel. We can also combine kernels in some way. Yes. So there's a question. Yes.
Yes. So can we also use a combination of kernel or multiplication? If yes, how are you going to choose, I mean, which kernel are you going to combine or to multiply in order to get the kernel for your problem?
So it's an excellent question. So we can combine kernels by summing them up and multiplying them. And so now finding the right combination of kernels is a combinatorial problem, which is very difficult to solve. So what you could do is you could start maybe by using a simple kernel, trying to model your data, and then everything that is not modeled with that Gaussian process, so the residual, you try to model as well. So I see you have an iterative procedure of like making your kernel more and more complicated. And that is something you could do. You could also write down immediately a sum or some function of different kernels, and then try to optimize the weights. So I'm going to actually look at this in the next example, where we have a function here, f of x, which is the sum of two different functions, which are a smooth functions and a smooth function and a periodic function. And we're going to use now a sum of two different kernels, which is the Gaussian kernel and the periodic kernel. And what we then will see is that by optimizing the marginal likelihood, we would find these the kind of like weight parameters, this theta s and theta p, that these parameters are found automatically as part of the marginal likelihood optimization. But in general, if you have a library, let's say you have 5 or 10 different base kernels, and then want to find a kernel that you can combine kernels either through adding or multiplication, or maybe even in some other ways. You want to find the best kernel that describes or that allows you to model your data set. Then searching that space of options is an absolute nightmare and very difficult to do. But there's some ways around this. Any other questions up to this point? Okay, then let's have a look at this example here. So we have training data, which is given by these blue crosses here. And the data is generated from a function which is a linear combination of a smooth function and a periodic function. And it's unclear to us, or we don't know what this kind of like what either the smooth function is, or what the periodic function is, or what these linear parameters are, the theta s and theta p. So, but we can now use a Gaussian process, which with a kernel, which is a sum of two kernels. One is the Gaussian kernel and one is the periodic kernel. And then we can add these kind of like theta s and theta p parameters to the kernels. So effectively, if you remember the equations of of the individual kernels, then the theta s and theta p parameters would be absorbed in the amplitude parameters, so that they are already weight parameters. So that means by optimizing the marginal likelihood, these theta s and theta p parameters would be automatically optimized as well. So now if we run our example again from before, you can see that the marginal likelihood value goes up. The fit of the function becomes, or say the distribution over functions becomes more reasonable. And this is kind of like what we find at some point. So this is the posterior distribution, or close to the posterior distribution of the GP. And so what happens here is that the amount of periodicity versus the smoothness is automatically chosen by selecting these hyperparameters theta s and theta p. So they are part of the optimization problem. And what we also see from here is that the marginal likelihood learns how to generalize and not just to fit the data. So it's another example of what we can see, that so data fitting is not the prime objective of the marginal likelihood, but the marginal likelihood also has the model complexity term in it. And at some point it will favor simpler models for more accurately fitting the training data. Yeah, so the fit is relatively good now. The model is relatively simple, but sometimes you can also see that the data fit term actually goes a little bit lower. So now it's going a bit lower, now it's going a bit higher, but the marginal likelihood value always goes up. So towards the end, I would like to look at some limitations and maybe some practical guidelines that may be useful if you work or when you work with Gaussian processes. So one of the big problems that we have in Gaussian processes is computational and memory complexity. So more specifically, if we have a training set size of n, then training scales cubically in the size of the training data set. Does anyone have an idea why that is the case? So when we, just to go back to maybe the training of the GP, right? So we optimize the log marginal likelihood, and that means we need to optimize this expression here. So what are the expensive things in this expression? What is expensive to compute here?
The inverse and the log?
Yeah, the log not. But the determinant is expensive, right? So the log determinant is expensive. So inverse, so how expensive is that?
Because you are taking the inverse depending on the size of the data set. So it becomes more computationally expensive because you are computing the determinant and finding the cool factor of the matrix, which becomes more expensive to compute. I don't know.
So no, it's a really good point. So the thing that we have here, right? So this matrix here is an n by n matrix, and so where n is the size of the training data set. And that means inverse scales in n cube. So computing an inverse is actually a very expensive operation. So that's one of the problems that we have here. Then the second one is that, okay, even assuming that we have trained our model, computing predictive distributions is also not super cheap. So it still scales quadratically in the number of data points. And we also need to store the kernel matrix, which is n squared, or the inverse kernel matrix. So that's is an n times n matrix, so n squared ballpark values we need to store. And we also need to store the data set. because we always need to evaluate the kernel at or compute cross correlations between f of x and f of x star. So storing that requires us n times d, where d is the dimensionality of the input data set. So in practice, you would not be able to run a Gaussian process in this form with more than 10,000 data points. And generally, we're talking about input dimensions of maybe 10, 20. So that's kind of like what you can do without paying any attention to any further details. But there's some work on that kind of like tries to address these issues to scale Gaussian processes to larger data sets. So there's some work on sparse Gaussian processes using something called inducing variables. So I don't want to go into details here, but these kind of methods in combination with mini batching and other things will scale Gaussian processes to millions or even billions of data points. So that is one way to get around or to address this issue of this n equals 10,000 limit. Okay, so there's a question. Yes, so parallelizing computation is an option. And so there is some work by James Hensman or Yarin Gal, where they do parallelizing or do parallelize computations. There are actually also, there's work by Andrew Wilson, which I haven't mentioned here. So they use modern compute hardware, so GPU clusters and incomplete Cholesky decompositions to scale full Gaussian processes, so exactly like this kind of thing here, to also relatively large data sets, I think like 1 million data points. So by using incomplete Cholesky decompositions, they would make approximations to the inverse kernel matrix that somebody mentioned earlier, which is the expensive part. There's also some work on running local Gaussian process expert models on subsets of data. So think about this maybe as if you have a very big data set and you just subdivide this into smaller data sets. Let's say each data set has maybe 1,000 data points. Then you could train a Gaussian process model on each of these individual data sets and then try to combine those predictions in the end. So that would also scale to pretty much arbitrarily large data sets. And there's also some work on variational Fourier features by James Hensman and colleagues, which also would address this issue of, at least to some degree, in low dimensions for that goes beyond 10,000 data points, training data points. So here are some tips and tricks that you can use, and again, I think we summarized this on the website here as well. You can use domain knowledge to set initial hyperparameters. That means if you have an idea of what your length scale parameter could be, you can initialize the hyperparameter to some meaningful value. You could think about standardizing the input data and then set the initial length scales to about 0.5. You could think about standardizing the targets and then set the initial signal variance to about 1. It is often useful in practice to set the initial noise level to relatively high values because the optimization surface becomes much smoother. So that allows you to simplify the optimization problem of the marginal likelihood to some degree. Random restarts is already something we mentioned earlier. And we could also, so sometimes we may be running into numerical instabilities. So we already had a discussion a little bit on Workplace a few days ago when you looked at the linear regression problem. Somebody was running into, or I think probably everyone was running into numerical problems at some point. So that can happen here as well. And if you actually look at the justification that we give here in this on the website, one way to address this issue is to have an extra penalty term on the signal to noise ratio, which is the amplitude parameter over the standard deviation of the noise value. So if you penalize this, then you have some sort of like regularizer in there, which would otherwise cause the Cholesky decomposition of the K plus sigma n squared I matrix to fail. So these are some tricks that you could that you can use when you implement Gaussian processes from scratch. I also want to maybe towards the end come back to some application areas that maybe where Gaussian processes are kind of useful. So Gaussian processes are used in reinforcement learning and in robotics, for example, to model value functions or transition models with Gaussian processes. Have you had a session on reinforcement learning already? Okay, cool. So that means when I say value function, that should ring a bell. And so if you can also do model-based reinforcement learning, where you learn the transition model using a Gaussian process. So these are options you can, or some things you can use Gaussian processes for. Bayesian optimization is another, I think, very prominent example of an area where Gaussian processes are used. So here the idea is to find high-level parameters of some bigger machine learning models, for example, learning rates in a deep neural network. You can use then Bayesian optimization or experimental design to find optimal learning rates. And here the idea is to model the utility function, unknown utility function with GPs. In this particular example, you can think of maybe you train a deep network with one particular learning rate or an initialization of a learning rate. You wait for a week, and then you can do some maybe some cross-validation to assess your generalization properties of the Gaussian of the neural network. So you can now think of this as a mapping that takes the learning rate to generalization error or cross-validation error. And there's a kind of like black box in the middle because you don't really have a functional description of how the learning rate directly influences the cross-validation error. And that kind of like black box you can model with a Gaussian process. And then you can use a Gaussian process to suggest your next experiment. So Bayesian optimization is something we're going to go through tomorrow. And so I'm going to go into much more detail tomorrow about how we can solve these interesting optimization problems using Gaussian processes. Gaussian processes, you may find that interesting, actually are an African invention. They came from South Africa, from Wits University. They were invented by a person called Krier. I think it's spelled like this. And so in the geostatistics literature, it's also called Kriging. So Gaussian process modeling is also called Kriging, and this was, I think, came from 1959. I'm not entirely sure whether that year is correct, but this person wrote a master's thesis on Gaussian processes for geostatistics. So I think it's pretty cool. And in the machine learning community, Gaussian processes only showed up in the 90s, right? So it's quite interesting. But because of the Gaussian process also gives it these kind of like nice error bars or uncertainty estimates. They're also useful for sensor networks. In the context of sensor networks, there's a lot of work on optimal sensor placements, for example, by Andreas Krause. But Gaussian processes are also used for time series modeling and for long-term forecasting, for example, in the context of climate science for weather and climate simulations. So that is maybe towards the end of the lecture. I wanted to give you maybe one motivating example of like where Gaussian processes are used in reinforcement learning and robotics. So I wanted to show you a little video of some work that we've done a few years ago, where we, can you see this?
Hello?
Yeah.
Yeah, Mark, I have a question on
Yeah.
the application. Yeah.
Yes.
So I would like to know if there is any work going on for Gaussian processing, natural language processing.
So in where?
In natural language processing.
Not that I know. So I haven't seen Gaussian processes in any kind of like NLP application yet.
Thank you.
Mm-hmm. Any other questions? Okay, then let me show you this little video that that we have here, where we use Gaussian processes for robotics, or for learning optimal control for robotic system in a reinforcement learning setting. So this thing is called a cart pole system. So you have a cart which is running on this track here, and we have a pendulum attached to the cart which is freely swinging. And now the idea is to push the cart, or to learn a strategy that pushes the cart left and right, that then swings the pendulum up and balances it in this inverted position in the middle of the track. And so what we use Gaussian processes for is we were collecting data from this system, so state observations, so that's the position velocity of the cart and the position and the velocity of the pendulum, and the control signals that push the cart left and right. And we were learning a transition model that predicts the next state distribution. And then we use this kind of transition model to evaluate the quality of a control strategy at the moment by computing long-term expected rewards. And then we use gradient descent to optimize policy parameters or controller parameters. So what it does, or what we did in the early stages, we're just like applying random actions to the system. You can see how this thing moves. And then we took these kind of data points that we collected, and so we had 50 data points at this point. We now trained this Gaussian process model for learning the transition dynamics. But as you have seen maybe earlier in some of the examples, 50 data points in a 4 or 5 dimensional space is not really that much, and that means we relatively quickly leave the range of the data. That means our predictive uncertainty will explode when we predict long term. But anyway, so we now use this model to predict the expected long-term reward and then optimize the policy, go back to the cart pole system and say, okay, here's a policy, try this one out. So this is what happens the first time. And here expected, so if you look at the variance, it's super useful to understand what happens. So what happened here was that after about maybe 2 or 3 time steps predicting into the future, we were optimizing about 30 or 40 time steps, the variances explode because we enter regions of the state space that we have not seen before. So the model is very uncertain, and then the variances explode and you don't have a meaningful learning signal anymore. But when you apply the controller, you now start collecting data in regions of the state space that you have not seen before. And that means the model that we now update with the new data is much more confident about what happened before. And so now it sees that what happened before was actually a pretty bad idea, and now it tries something else. So again, we use this updated Gaussian process model to compute a long-term reward, and then it finds something else, right? So now it has the idea of like, or got the idea of swinging the pendulum up. But it also now has, for the first time, it actually had data in this regime where things are interesting, right? In a state space where the pendulum was kind of upright, but it was far too fast. But the reward also says, you know, you were far too fast, do something about it. And now we can see over the next couple of trials that it takes this information into account. So every time it runs one of these trials, it updates the Gaussian process model. The Gaussian process model becomes more confident. And with a more confident model, maybe also get a better control strategy. And then after a few trials, I mean, you can really see like an improvement in every trial compared to the previous trial. And with about 15 seconds, it kind of like gets the idea of like swinging the pendulum up and balancing it. And we can run this for a little bit longer and see that it actually solved the problem. So there's no, so we, and the Gaussian processes we use are the ones we discussed in this lecture. So we use a mean function, which is, I think it's linear. And we used a squared exponential or a Gaussian kernel that that we discussed to, I think, in pretty much, or in a lot of detail in this lecture as well. So there's nothing fancy actually going on. Okay, there was a question.
Hello, Mark.
Yes.
Yeah. So, but what's now the advantage of using the Gaussian process in reinforcement learning as compared to other classical approaches to solving optimal policy in reinforcement learning?
So it's much faster. So you saw that, you know, we needed like 5 or 6 trials or 7 trials to solve this problem, or maybe if you look at the number of the experience or that we need is like 20 seconds of data. And if you compare this with, for example, Q-learning, then we are orders of magnitude faster. So that means you can actually run this kind of reinforcement learning on a physical system, such as a robot, where you have practical constraints of how many experiments you can run or how much data you can collect. So that's a reason why this is very interesting.
Okay, so but based on my little understanding about reinforcement learning, you know, every approach has its own advantage, and as in terms of the domain where you can apply it compared to others. So and I believe the Gaussian process also we have where we can actually use it and where it won't be a feasible solution, feasible approach for us to take. Can you just elaborate more on that?
Yes, so the Gaussian process is super useful if you have relatively small data sets. I mean, you already know that, you know, when we go beyond 10,000, then things become a bit tricky. In a reinforcement learning, I mean, we can use sparse approximations, but I think relatively small data sets is a regime where the Gaussian process works relatively well. The second one is the dimensionality of your input features. So we haven't really solved the problem of like working on images yet. So I would say input dimensionality in an RL problem is limited to, say in practice, maybe 10 to 20. We have successfully solved like higher dimensional problems, like maybe around 30 dimensions. But that's, you know, these are the ballpark numbers you will need to work with if you do this. And the third constraint is that we need to choose kernels that allow us to model the underlying function relatively well. And so in many cases that may be fine, but there are some cases or some functions that where the Gaussian process will have difficulties modeling the right thing. And these are things where you have, you know, relatively smooth behavior of the function, let me just draw an example on this slide here. So if your function looks like this, and then you have a jump. So this kind of function is very difficult to model. I think for anything, even a neural network will have problems with this. But if we try to model functions like this in an RL setting with a Gaussian process, we will have problems. And then I think the RL wouldn't work that well. So if we have smooth functions in relatively low dimensions, then I think the Gaussian process is a very good choice for doing model learning in reinforcement learning. And otherwise, we may have to think a bit more carefully about what to do.
Okay. So,
yeah, so I'm
lastly,
sorry. Yeah, please.
Okay, go ahead.
No, please ask.
So, lastly, I want to just just asking you if you have, are you exploring any other approach using reinforcement learning with Bayesian
Bayesian models?
Yeah, Bayesian model, yeah.
So there are some approaches that look at ensemble methods. Bayesian neural networks or ensembles of neural networks or ensembles of functions. So you still have some sort of distribution over functions. So these are other approaches that could be used in the context of reinforcement learning.
Right, thank you.
Okay. Okay, so Daniel is saying this looks similar to the card pole problem. Yeah, so that is exactly the card pole problem that we were looking at earlier. Daniel, does that answer the question?
Yes, please.
Okay. Yeah, so I'm happy to talk much more about this kind of work in RL if you are interested in, but we should probably take this offline or maybe talk about this Friday afternoon after the test. So, but let me quickly summarize what we talked about in the last 2 days. So Gaussian processes are, I would say, the gold standard for regression problems. And the reason for this is that they give us reasonable error bars. They are closely related to linear regression, but they automatically trade off data fit and model complexity through the marginal likelihood. And that is actually a really nice thing that the Gaussian process does. While the theory is potentially a little bit difficult to understand, when we actually do our computations, the only thing that we need to do is we need to be able to work with multivariate Gaussian distributions. So there are 2 things that we need to be able to do, and one, or maybe 3 things. One is being able to multiply Gaussians together, to condition Gaussians or multivariate Gaussians or joint distributions. And the third thing is to be able to marginalize. So these are the 3 things that we need. And when if we know how to do this, and we can do everything that we discussed today with Gaussian processes. And I also really wanted to make a point about the marginal likelihood as a useful objective that trades off data fit and model complexity. So that's kind of like the end of today's lecture. I have a bunch of references in here, so if you're interested in looking at some of these things, I'm also happy to provide more literature if somebody of you is interested in Gaussian process stuff. And so I think that's it for today. Are there any questions? Okay, so
Mike.
Yeah.
Sorry, the annotated slide that you uploaded yesterday for part 1, I think there was no annotation there. You uploaded the previous one you uploaded.
So I re-uploaded this morning. So can you have a look at this again, please? It should be there, and I'm gonna upload the annotated version of this also this afternoon.
Okay, thanks.
Yeah, I have a question. Is there any limitation that's imposed by the dimension of the feature vector in case of GPs?
Theoretically not, in practice, yes. So the thing is that if we go to higher dimensions, if we want to actually model anything in a meaningful way, we also need more data. So for example, if you look at a 1,000-dimensional space, if you only have 10 data points in 1,000 dimensions, that's pretty meaningless. So in order to fill a 1,000-dimensional space, you probably have to look more at like billions of data points. And then we run again into the problem of the compute and memory problems that we have with the Gaussian process. So the equations only scale, I think if I'm not totally wrong, scale linearly in the dimension, but it scales cubically in the number of data points. And so in higher dimensions, we typically need more data points. So this goes hand in hand.
Okay, so that's the case with cost of dimensionality.
Yes, exactly. The curse of dimensionality will kick in here as well.
Okay, thank you very much.
Yeah. Okay, so there's okay. I'm going to stop the recording here, and then I can answer some more questions.